Welcome everyone to the 2026 Integrated Photonics Summit. Thank you all so much for joining us, and in this session you'll hear from Susanne Hartmann, a research and development engineer at Scia Systems. Suzanne earned a master's degree in physics from Chemnitz University of Technology in 2015, completing her thesis within the Semiconductor Physics Research Group. Today she joins us to highlight reactive ion beam etching of PIC materials with high optical performance. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen, and if you missed part of today's sessions, you can always come back later and watch them on demand. That's all from me. Suzanne, we appreciate you for taking the time to join us here at the Integrated Photonics Summit.
Okay, thanks for the kind introduction and welcome all to my talk on the etching of lithium niobate for photonic applications with reactive ion beam etching. In this talk, I will quickly introduce to you who we, Scia Systems, are. I will tell you why we're interested in photonics, and I will share with you the materials of lithium niobate and results of etching. Scia Systems is a company that is specialized in ion beam and plasma technologies. For example, we produce machines for the etching and decoding of wafers up to 300 millimeters diameter in size, but we also develop customer-specific solutions, so for example, CMOS-compatible equipment. We're located in Germany in a small city close to Dresden, and with over 200 employees, we build our machines on 9,000 square meter floor space. Out of this space, there's 1,800 square meter ISO 7 clean room, and within this clean room, we have a small measurement lab that fulfills the quality of ISO 5, so it's even better, so demos can be held with even better quality. Why are we interested in photonics? Well, we all know about the hype of the artificial intelligence, and within 2020, we have generated as much as 64 zettabytes of data, which is an unimaginably high number, and it means that there's 10 terabytes of data per person on Earth. If we calculate this down, this means that as much as half a zettabyte of data is being produced every day, and this is clear that the bottleneck is the bandwidth here. If you take into account that each question to the artificial intelligence costs as much as 10 times the power that a simple question to Google does, it is also clear that the electrical power consumption of the artificial intelligence in the data centers is not negligible anymore. Talking about data centers. When we have data centers, 10,000 of racks need to communicate with each other, and this means that we have cable lengths as long as 2 kilometers. If we had copper cables as long as this, we would have lots of ohmic losses, we would have lots of heat dissipations, and furthermore, long copper wires would work as antennas, so we would have electromagnetic interference. All of these bring us to photonics, so working with photons in glass fibers, which do not have these issues at all. Furthermore, when we have the bandwidth in electronics, we are working at gigahertz bandwidth, but with photonics, we can work at terahertz bandwidth. So we can compute as much higher speed without additional cost. And last but not least, we can superimpose different wavelengths, so one circuit can have many parallel applications. When I was talking about fibers, that's a macroscopic scale, but of course, this also works on microscopic scale. So still replacing the integrated circuits, we can replace them with photonic integrated circuits, where still photons transfer the data instead of electrons. And now we do not use copper anymore as conductors, but we use so-called waveguides as conductors for the photons. For waveguides, we need new materials, which I will tell you on the next couple of slides. And of course, these photonic integrated circuits can be integrated alongside the traditional electronics in so-called co-packaged optics. Which materials can be used for photonic integrated circuits? Well, traditionally, we had silicon as a good material, but silicon has very rough sidewalls when we etch it. Thus, we have huge optical losses. If you compare that with silicon nitride, it has much smoother sidewalls. Thus, the optical losses will be much smaller. However, both of these materials, they do not have any Pockels effect. Why do we need a Pockels effect? The Pockels effect implies that an electrical voltage can influence the refractive index of our material such that the electronic signal can be transferred into an optical signal. This is why a very strong Pockels effect is good to transfer electronic signals into optical signals. That's why we are interested in lithium niobate, so LN, or TFLN, thin film lithium niobate. Even more, there are new materials emerging into the market, such as barium titanate or BTO, which has a very strong Pockels effect and is even better than lithium niobate. However, these processes are not yet as developed, so they need to be developed further. That's why in this talk, I want to talk about lithium niobate as material for photonic integrated circuits. Let's recapitulate again which advantages we have from the lithium niobate. As I mentioned already, we have a huge electro-optical coefficient, so the Pockels effect. It has a high optical nonlinearity, and it has a wide transparency window from 400 nanometers to 5 microns in wavelengths. So it is applicable for very different applications. How is LN being used at the moment? The state of the art is so-called titanium in diffusion. In this case, we have lithium niobate all over the place, and on top of this, there's a structured area of titanium, which is then by annealing diffused into the lithium niobate. By this, we have a local change of refractive index, which defines our waveguide. However, this change of refractive index is relatively small, so we need still very large turning radii for our devices to avoid bending losses. This means that we have a huge device size and higher power consumption. This is why we want to go to different techniques, such as rich waveguides, where now the dark area is the lithium niobate, so the lithium niobate is etched through on top of a substrate. There's also the possibility of not etching the lithium niobate through, for example, in so-called RIBE waveguides. Now, how do we etch the lithium niobate? Traditionally, of course, there's wet etching possible. However, wet etching is an isotropic process, thus it causes under etching. This is not applicable for small feature sizes. Also, it is relatively rough and causes optical losses at the sidewalls. Another possibility would be plasma etching. However, this also causes sidewall roughness and optical losses. We are instead working with ion beam etching and even further with reactive ion beam etching, where we try to develop very steep sidewalls with hardly any redeposition, which I will show you later. To sum up, we are working on the etching of lithium niobate for the rich and the RIBE waveguides. Let's step one step back. How do we get such waveguides? For optimized light transmission, we not only need smooth sidewalls, but we need an optimized dimension according to the wavelengths of your application. This means that we need a thickness control of the layer of our lithium niobate, which can be done via ion beam trimming. And we need the width control of our structure from the mask into the lithium niobate. So the structure fidelity is important, which can be done with ion beam etching. Let's first step into the ion beam trimming. In ion beam trimming, we see on the right-hand side, on the upper part, the machine that can be used to do so. We have a load lock at the front where a wafer cassette can be placed with 25 wafers. Then there's a transfer module where the wafer is handled in and the notch or the flat is aligned. And then we have the main chamber here. At the bottom, we see how this actually works. So the ion beam has been focused on a small area of roughly 1.5 centimeter diameter in size, and then it's raster scanned along the wafer. Now we can control the dwell time to control the removal to have a uniform pattern afterwards. So if we look at this example over here, we see a non-uniform wafer map before the etching, and after the trimming, we see that the wafer is very, very uniform. If we go to application of lithium niobate, we see here a wafer map beforehand, which had a structure height of 579 nanometers of lithium niobate with a height variation of 3.84 nanometers and standard deviation, and this was decreased to a target height of almost 540 nanometers with only 0.2 nanometers deviation, and the standard deviation was decreased by a factor of 3. So now it is much more uniform and can have a much higher yield for our applications. Coming to the etching with the ion beam, with the broadband ion beam. Coming to the ion beam etching, on the right-hand side, we see the tool that is used for this application. We again see the load log on the left-hand side, where the cassette has been placed. We see the transfer module, where the wafer is aligned, and we see the main chamber. On the top, we see the turbo pump, because of course the machine is in high vacuum. What we do not see is the ion beam source, which is pointing to the backside. What you can see in the animation is that the wafer is handled in horizontally, and first from the handler, and then it can be rotated to arbitrary angles. For example, it can be etched at a perpendicular angle between the ion beam source and the wafer, or it can be etched at any arbitrary angle, which we will see later. The ion beam source itself has a diameter of 362 millimeters, so it is much larger than the 8-inch wafer that can be etched in here. So we have a very uniform etching. Also, for the uniform etching, the wafer is rotated all the time. And not only this, we can also do reactive ion beam etching within this machine. I want to introduce to you this topic a bit further. So when we go for ion beam etching or ion beam milling, we have an ion beam that is created within the plasma from an inert gas such as argon or krypton. This ion beam has been extracted by a free grid system so that then physically the wafer has been sputtered by argon ions. In reactive ion beam etching instead, we don't only use argon for the gas within the plasma source, but we also introduce a fluorine-containing gas, for example, such as CHF3 or SF6. So this creates within the plasma reactive species. And then we have different ions that not only physically etch the wafer, but also chemically. So selectivities can be much increased, as well as etch rates. And last but not least, we have CAIBE, chemically assisted ion beam etching, where we have a gas ring, which is close to the wafer, and we insert a chlorine-containing gas, which is chemically reactive by itself. So it etches already the wafer, and this etching is then enhanced by the argon ion beam, so it etches much, much faster. But in this talk, I want to talk to you about the reactive ion beam etching with fluorine-containing gases. Before I come to some results, I want to introduce to you some vocabulary that I will be using later on. And there's the so-called fencing. For example, when we have here a cross-sectional image from SEM, from scanning electron microscopy, where the bright area is the lithium niobate, and on top of this we have a dark area of the mask that has been used for the etching. We see here on the right and the left-hand side of the mask these bright fences, so-called fences. And these fences come from the resputtered material from the lithium niobate. So it's lithium niobate that's been deposited at the sidewalls of the mask. And we want to avoid this as much as we can by either having a mask as thin as possible or by choosing processes that do not create fences at all in the first place. Another artifact is the so-called footing, which you can see over here, that we do not have a perpendicular foot, but this kind of shape. And this happens due to too shallow angled etching, which then causes some kind of shadowing effect. When we can etch too shallow, we can also etch at too steep angles, which is the so-called trenching, where we have this small trench over here, which comes from reflected ions back from the mask. So the idea is to change the tilt angle of the wafer with respect to the ion source, and with this we can switch from footing to trenching and in between. And then we have the mask erosion, which often happens for photoresist masks, which then behave differently in the ion beam, so not like expected. And then we can have artifacts on the edges. And last but not least, there's the so-called curtaining effect, which happens due to the roughness of the mask, which is then transferred as the roughness of the lithium niobate itself. So we have lots of optical losses due to this, which we want to avoid. Now, this is the mask that has been used for the lithium niobate etching. So this is the before image, so to say. These results were obtained with an institute from Canada, C2MI, where we have a silicon oxide hard mask on top of a lithium niobate layer, and you can see that the sidewall angle is very high. It is very good with 84 degrees. Now we want to etch this lithium niobate with reactive ion beam etching. And as I told you earlier, I want to vary the gas flow of the reactive gas with respect to my argon gas flow, and I varied it from low over medium to high. And when we look at the etch rates in the first place, we see that the silicon oxide etch rate increased a lot, whereas this lithium niobate etch rate hardly changed at all anymore. So the selectivity, in fact, got worse, which is not what we wanted and not expected, because the lithium niobate was not volatile in higher gas flows. When we look at the sidewall angle, we see that the steepest sidewall angle was gained at a medium gas flow of the reactive gas. And if you look at the bottom images, so these are again cross-sectional images from scanning electron microscopy for the low, the medium, and the high content of the gas flow, of the reactive gas flow. And we see for the high gas flow that the sidewall angle is in fact very shallow. So this is not what we want. Instead, we rather want a low or medium content of the gas to have a very steep sidewall angle. But what we see here in the bottom is a small foot. That's why in the next stage, in the next slide, I will show you a tilt angle variation between the wafer and the ion beam source to switch between the footing and the trenching, which I introduced to you earlier. And this is what I did over here. So I varied the tilt angle from 0 degree to 25 degree. I did not always determine the etch rates, but when we look at the sidewall angles, what we see over here is that we get the best sidewall angle at about 15 degree tilt angle. When we look at the images, we see that for the small tilt angles, we see a small trench over here, and for the larger tilt angles, we see a foot evolving. So the best tilt angle, in fact, would have been right between 5 and 15 degree tilt, which unfortunately I did not etch. If you look at the bottom images, these are from the backscattered electrons in the scanning electron microscopy. And we see that there's a bright area right next to the mask over here. And this bright area is the fence that I introduced to you earlier. So it's redeposition of lithium niobate, which we want to avoid. And how do we avoid it? We choose a two-step etching process over here. So we leave the first step etch at the 15 degree tilt, which was optimized now. And now we introduce a second step, which is at a more shallow angle, and thereby it etches the sidewalls of the mask in order to remove those fences. And this is what I did in the next slide. So I increased this second step from 0 minutes to 3 minutes, the so-called sidewall clean steps, SWC. And what we see is that if we look at the bottom images from the backscattered electrons, that the fence height, which was initially very high, was then decreased a lot, and finally it was removed at all. However, at the same time, we lose sidewall angle. It is more shallow now. So, summing up this slide, we can remove the fences from the redeposition of the lithium niobate. However, this is at the cost of the sidewall angle. To sum up my talk, I would like to say that I showed you reactive ion beam etching of lithium niobate for photonic applications. I could switch between footing and trenching, and we could remove the fences by a two-step etching process. However, we still don't have an optimized sidewall angle, so we want to analyze multi-step etches further in the next step. Also, we want to replace the silicon oxide hard mask with a diamond-like hard mask, which is much harder, and thus a thinner hard mask can be used. Thereby, we try to avoid the fences even further. And last but not least, we have cooperations with different partners where we also want to do optical measurements to define how high our optical losses are at the moment. With this, I'm at the end of my talk, and I would like to thank my colleagues for their support. And of course, I would like to thank you for your attention.
And Susanne, thank you so much for introducing reactive ion beam etching of PIC materials. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can type your questions and comments into the Summit chat box. And do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Integrated Photonics Summit. Thank you all so much for joining us.